Let's try it by dropping a soccer ball and a truck and see what happens. As you can see, they hit the ground at the same time. In fact, all bodies on Earth are pulled towards the ground with the same acceleration, 9.8 meters per second squared, no matter how heavy they are. However, objects that are very lightweight or have a large surface area, like a piece of paper or a feather, will be slowed down by friction with the air. If you take away the air, they fall just as fast as a rock. This is a general rule about gravity. Everything on the surface of a given world will be pulled down with the same acceleration. That acceleration will be different for each world, though. For example, on the moon, the acceleration is less, so things fall more slowly there. You can click on a link to see this being demonstrated by the folks on the Apollo 15 mission to the moon back in 1971. In the 1600s, Isaac Newton figured out the law of universal gravity. I could just give you the formula here, but I think you should get a chance to see how Newton came up with this equation. It's not that difficult to see where most of the parts come from. The first step is to start with a basic observation. Everything feels the pull of gravity. In other words, the gravitational force acts on all matter. However, think for a minute about Newton's third law of motion. For every force, there is an equal and opposite reaction force. So if every bit of matter feels gravity, then every bit of matter must also have its own gravitational force. That's why we call this the universal law of gravity. It's universal because all matter exerts a gravitational pull. Planets, moons, stars, buildings, people, guinea pigs, and so on. We all have our own gravity. So now let's figure out how strong this force is. We'll call the force of gravity F sub g. F for force and g for gravity. So we can start by saying that the gravitational force is equal to something. We're just not sure what. If everything experiences a gravitational pull, try holding a ball close to your head and then let it go and see what happens. Of course, the ball will be pulled to the ground, not to your head. So why is that? Right, the Earth is a lot bigger than your head is. This means that the gravitational pull must depend on how big something is, or more accurately, how much mass it has. So we can say that the gravitational force the ball feels depends on the mass of the thing pulling on it. Let's write this out as gravitational force equals something times m sub 1. Next, think about what we just said about falling bodies. Everything falls with the same acceleration. Imagine that instead of dropping a truck and a soccer ball, you are trying to push them instead. You know from Newton's second law that if you want to push the truck, it takes a lot more force than it does to push the soccer ball, because the truck has a lot more mass. That must be what's happening with gravity. If a giant truck gets the same acceleration as a ball, then the truck must feel a much larger gravitational force than the ball. If it were the same force, the ball would race toward the ground, while the truck would just sit there, floating in midair, hardly moving downward at all. So the force depends on the mass of the thing being pulled, as well as the mass of the thing pulling. We can write this down by saying that the force is equal to something times mass 1 times mass 2. Let's think about that ball again. We know that when we drop a ball, it falls to the ground. Now, the planet Jupiter is 300 times as big as the Earth. But somehow, even when Jupiter is high in the sky, we never have to worry about the ball falling towards Jupiter instead of down to the ground. Why is that? Of course, Jupiter is far away, so gravity must get weaker as objects get farther apart. We can write this by saying that the force is equal to something times the two masses and divided by the distance. Note that this is distance, not diameter. But what distance? Is it the distance between the surface of the ball and the surface of the Earth? Try this experiment. Set the ball on the ground. At this point, the distance between the surface of the ball and the ground is 0. If you put a distance of 0 into the formula we've got, you'll find that whatever masses are there no longer matter, because the force blows up to infinity and the ball should be stuck to the ground forever. Since you can pick the ball up off the ground, the distance in the formula can't be between the surfaces. In fact, the distance we need is between the centers of the objects. If you want to know the force between the ball and the Earth, you use the distance between the center of the ball and the center of the Earth. Since the Earth is much bigger than the ball, this will usually be simply the radius of the Earth. We've almost got the law of universal gravity. There are just 2 more things we need to do. First, when we actually calculate how the force behaves, it turns out that it gets weaker with distance even faster than what we have here. In fact, it drops off with the distance squared instead of just the distance. Secondly, we need to put something in there to get the units right. We've got force units on one side of the equation, and we've got mass squared divided by distance squared on the other side. They need to match up. So we put in something called the gravitational constant, capital G. We'll look at this more closely on the next slide. That's Newton's universal law of gravity. The force of gravity between any 2 bodies depends on both of their masses and the distance between them squared. Let's look a little more closely at the gravitational constant. First off, it's a universal constant. The gravitational constant is the same on the Earth as on the Moon and anywhere else in the universe. Its value is 6.67 times 10 to the minus 11 meters cubed per second squared kilograms. So anytime you see this in a formula, you know what you'll have to put in. You don't have to memorize the value, though. I'll give it to you on exams. As I said on the last page, this constant makes the units match up. This is the part that tells you how much force you get from 1 kilogram masses at 1 meter distance. At the same time, this forces you to use certain units. Anytime you see the gravitational constant in a formula, you know that all the rest of the units in the formula need to match up with this. So masses have to be in kilograms, distances in meters, and times in seconds. If any of the values you are given are in different units, you'll have to convert them before you can calculate, or you will get the wrong answer. Finally, let's think about what the gravitational constant actually means. That negative exponent tells you that the constant is small, meaning that the force of gravity must be incredibly weak. In fact, it's the weakest force we know of in the universe, much weaker than the other force we experience regularly, the electromagnetic force. To appreciate this, think about standing up. The gravity of the entire Earth, 6 times 10 to the 24 kilograms of it, is trying to drag you into the ground. However, just a few kilos of bone are able to resist the pull of the entire Earth and hold you up. Those bones get their strength from the electromagnetic forces in the atoms. So gravity is weak. The only reason we notice it is simply that it adds up. There isn't any negative gravity. So the gravity of the entire Earth can combine to pull on you all at once. On the other hand, electric forces come in positive and negative charges. So most of the time, they cancel each other out.
There's one last thing about the law of gravity that we want to point out before we go on, and that's a philosophical point about scientific method. Notice how Newton worked. He based his 3 laws of motion on observation of the world around him. He developed his law of gravity by assuming that the laws of motion applied to parts of the universe that were beyond his ability to observe or measure. Above all, he was trying to develop a law of gravity with logical consistency. The force of gravity that an object feels should be the force that free-fall acceleration indicates. This logical, consistent thinking is characteristic of the way scientific theories are developed, and this is one of the times in the course where we discuss all the steps in the process. So what is the next step in the scientific method? You should know that by now, but if you don't, go back and take a quick look at the science section. Or your instructor may assign a discussion of this question as a your turn. If so, you may also be asked to consider whether this is a step that Newton himself could take. Do you think it's a step that could have been taken in Newton's own lifetime?